This is a device that's able to measure BPM. So let's to check the component of the device. So definitely the first thing you need is a microcontroller. So this is Cortex M, that's Texas Instrument, actually the Launchpad T-C series. That's very cheap board. You could buy around 10 bucks. So the next component is the sensor. So the heart rate sensor, I bought that for just for 2 bucks from the eBay. So I just fixed that around my finger. I actually tape it on my finger. So this is actually exactly the sensor that you see. So, and the next is the LCD. The LCD that I use to indicate BPM is actually Nokia 5110. So that's actually another cheap LCD. I bought that around 10 bucks from the eBay, or you could buy in the same price for any other website. So the device is actually measure the BPM. So if you reset the device, that I'm going to reset that. So it's actually show this message, please wait. So definitely device need 1 minute to give you a BPM, right? The BPM is beat per minute. So definitely you need a 60-second or 1 minute, and you need to count the heartbeats that you have. Then you are able to actually calculate the BPM. So for that reason, whenever you reset the device, definitely it should give you a message, please wait. And actually the device need 1 minute, then able to indicate the BPM on your LCD. So as I already mentioned, this is very cheap LCD you could buy. This is Nokia 5110, around 10 bucks. You could buy around the 10 bucks. But if you don't have, you could just use the print serial port and print your output on your screen and just able to see that. So as you could see here, after 1 minute, it's actually indicate the BPM. So right now my BPM is 80. So as you probably know, the BPM usually is the number between 60 to 100, and right now is my BPM is 80. So let's see how we could make this cheap BPM device. So let's see how we could measure BPM. So we start actually with the very simple circuit. So we connect our sensor to our microcontroller. For my case, microcontroller is a launchpad. The launchpad actually has the 12-bit analog to digital converter, so directly connect through one I/O pins. So we use the Energia and use one simple function that's able to read that analog signals from the sensor. So as you could see here, we use the analog read. You read whatever you have here as your pin. So then you actually save that inside one variable, and then you just use the serial println and just print that value. So very simple code. You just plot or actually print the value or the output of your analog to digital converter and see what we will get. So what you see right now is we actually plot the output of analog to digital converter, so without any filtering and without doing any actually processing. So that means you just read the analog to digital converter, you connect the sensor, so to the analog digital converter convert the analog signals from sensors to the digital number. You just directly plot that. So as you could see, you have actually the sensor, which is the heart rate sensor, and this is what you see on your as an output of your sensor. So as you could see, if you actually somehow stop this, you could see that actually the heart beats, but it is very noisy. It's actually changing the DC level a lot. There is actually the baseline wandering. So definitely there is nothing actually useful over there. at least if you don't do any actually signal processing on these raw signals that you have. Okay, so definitely we need to actually some filtering on this that able to have some useful signals that we able to use. So I could see that spike on the signal. So see, you could see these spikes that you have. Definitely they are the heartbeat, but as you could see, that's very noisy. There is actually the huge baseline wandering over there, which is technically you couldn't see anything useful on that. So what we are going to do, we are going to actually take 20 milliseconds of these signals and take the average of that point. So that means you cut the signals in 20 milliseconds and take the average of the whole data that you have. So then you actually plot that average point. So definitely it's helped you to somehow dismiss the signals and also get rid of some noise, especially whenever you use the 20 millisecond. Definitely you should able to get rid of the 50 hertz actually noise that you have. So let's do that and see if we actually do that, what we are going to get. So as you actually saw, whenever you actually use the simple circuit, if you just plot or consider the output of the analog digital converter, so your signal is really noisy and really you couldn't, it's not clear the heartbeats actually signals, and definitely you need some signal processing that able to get the clean signals. Then you able to consider 60 second, 1 minute, and count the number of the bits inside that and able to calculate BPM. So this is actually technically doesn't work. Actually you saw the signal. So what we are going to do as a second step, we actually use the filters. So what we want to do here, so we actually connect our sensor similar with the step 1 to our microcontroller. So we have these signals here, which is the output of this analog to digital converter, which was very noisy. So we are going to actually, whatever you got here, so we are going to consider some time interval on the signals, and that time interval is 60 milliseconds. So then take average of that 60 millisecond and you just got 1 point average or mean for that 60 millisecond. Okay, so that means for here to here you actually read all of them. So then take average, just consider that 1 point you could save inside the array. So then you are doing that for the whole that 60 minutes time interval. That means the next point comes from the another 60 minutes time interval. The next comes from the third actually point is the third 60 minutes time interval. And then you use actually the same serial println, but this time you are actually plotting or you actually printing the value of these average point. So this could be actually 20. You also use here I use the 60 minutes, so you could use 20 minutes to 20 milliseconds too. Whenever you use 20 milliseconds, so technically you are smooth your signal and also you get rid of 50 hertz actually noise. So here we use 60 milliseconds and let's see what we will get. So instead of actually plotting directly the value that you got from the analog to digital converter, first you consider the 60 millisecond time interval, take the mean of that, and then you plot the average points and let's see these techniques able to smooth our signals and getting more clear and smooth signals. So let's see what we will get if we will do that. This is our signal after actually you implement the smoothing algorithm. So as you could see here, it's right now you see very clean signal. So this is actually the output of our sensor. So what we did, we actually take the average in every 20 millisecond, then plot that average. So which is somehow you get rid of the noise, and especially 50 Hz noise, and also you make your signals more smooth. So as you could see here, this is very clean and acceptable signal. So for calculate the BPM right now, you just need to actually have an algorithm that able to detect these peaks in 60 seconds, and the number of these peaks in 60 seconds, that will be your BPM, which our algorithm able to do that. Our algorithm actually detect these peaks and calculate the number of that peaks in 60 minutes, then print that number on the LCD or on your COM port that you have. So unlike the first plot that we had, so right now we actually made our signal more green, more smooth, and more stable. So even if you want to use some algorithm for detecting the peaks with base of the threshold that you have, you see your signal is stable. So right now I'm moving my finger, so probably you couldn't see that, but I move my finger. So see, even if you select some threshold here, I don't know, for example, 2050, so something around this, okay? So I'm actually right now moving the sensor and moving my finger. So you see there is no baseline wandering. So it just shows how good your algorithm is. So if you use the threshold and whenever you move the sensor, the baseline, you have actually changing in the DC line, or you have the actually baseline wandering, so that should be a problem for your algorithm because it works based off the threshold. So but right now you see I actually move my finger, and definitely if you set these 2050 as your threshold in your peak detection algorithm, definitely even if the person move his finger, so definitely you have no problem. So and the signal is a very stable and acceptable signal.